Are you ready to dive into the world where data rules? Welcome to our thrilling exploration of the fundamentals of data systems. This isn't just any guide, it's your ticket to mastering the concepts that drive today's most innovative applications. Let's first understand various needs of today's application. Databases store data so that they, or another application, can find it again later. Caches remember the result of an expensive operation to speed up reads. Search indexes allow users to search data by keyword or filter it in various ways. Stream processing send a message to another process to be handled asynchronously. Batch processing periodically crunch a large amount of accumulated data. Based on the above needs, we have understood that many applications today are data intensive as opposed to compute intensive. Raw CPU power is rarely a limiting factor for these applications. Bigger problems are usually the amount of data, the complexity of data, and the speed at which it is changing. We typically think of databases, queues, caches, etc. as being very different categories of tools. Although a database and a message queue have some superficial similarity, both store data for some time, they have very different access patterns, which means different performance characteristics, and thus very different implementations. If you are designing a data system or service, a lot of tricky questions arise. How do you ensure that the data remains correct and complete, even when things go wrong internally? How do you provide consistently good performance to clients, even when parts of your system are degraded? How do you scale to handle an increase in load? What does a good API for the service look like? We can divide these concerns under three categories: reliability, scalability, and maintainability. When we talk about reliability, in software terms, our expectations might be: the application performs the function that the user expected. It can tolerate the user making mistakes or using the software in unexpected ways. Its performance is good enough for the required use case, under the expected load and data volume. And the system prevents any unauthorized access and abuse. Let's understand what is a fault. The things that can go wrong are called faults, and systems that anticipate faults and can cope with them are called fault-tolerant or resilient. Several faults can lead to failures. First, we need to understand the difference between a fault and failure. Note that a fault is not the same as a failure. A fault is usually defined as one component of the system deviating from its spec, whereas a failure is when the system as a whole stops providing the required service to the user. It is impossible to reduce the probability of a fault to zero, therefore, it is usually best to design fault tolerance mechanisms that prevent faults from causing failures. There can be various kinds of faults: hardware faults, software errors, and human errors. Let's discuss them one by one. Hardware faults. When we think of causes of system failure, hardware faults quickly come to mind. Hard disks crash, RAM becomes faulty, the power grid has a blackout, someone unplugs the wrong network cable. Anyone who has worked with large data centers can tell you that these things happen all the time when you have a lot of machines. Hard disks are reported as having a mean time to failure, MTTF, of about 10 to 50 years. Thus, on a storage cluster with 10,000 disks, we should expect on average one to die. Knowing these facts, our first response is usually to add redundancy to the individual hardware components in order to reduce the failure rate of the system. Disks may be set up in a RAID configuration, servers may have dual power supplies and hot swappable CPUs, and data centers may have batteries and diesel generators for backup power. However, as data volumes and applications, computing demands have increased, more applications have begun using larger numbers of machines, which proportionally increases the rate of hardware faults. Moreover, in some cloud platforms such as Amazon Web Services, AWS, it is fairly common for virtual machine instances to become unavailable without warning. Considering these factors, there is a move towards systems that can tolerate the loss of entire machines, by using software fault tolerance techniques in preference or in addition to hardware redundancy. Software errors. The problem of systematic faults in software has no quick fix. Several strategies can help. Carefully consider assumptions and system interactions. Conduct thorough testing. Isolate processes. Allow processes to crash and restart. Measure, monitor, and analyze behavior in production. Systems should self-check for consistency. They should alert on discrepancies. Now, let's discuss human errors. Human errors. Humans design, build, and operate software systems. Despite good intentions, humans can be unreliable. Configuration mistakes often cause outages. Mitigating human errors requires intuitive systems. Provide thorough training. Automate tasks to reduce mistakes. Design systems to degrade gracefully. Having discussed reliability, let's now turn our attention to scalability. Scalability is the term we use to describe a system's ability to cope with increased load. First, we need to define load. Load can be described with a few numbers, which we call load parameters. The best choice of parameters depends on the architecture of your system. It may be requests to a web server, the ratio of reads to writes in a database, the number of simultaneously active users in a chat room, the hit rate on a cache, or something else. Once you have described the load on your system, you can investigate what happens when the load increases. You can look at it in two ways. First, when you increase a load parameter and keep the system resources, CPU, memory, network bandwidth, etc., unchanged, how is the performance of your system affected? Second, when you increase a load parameter, how much do you need to increase the resources if you want to keep performance unchanged? In a batch processing system such as Hadoop, we usually care about throughput, which is the number of records we can process, or the total time it takes to run a job on a dataset of a certain size. In online systems, what's usually more important is the service's response time, that is, the time between a client sending a request and receiving a response. Latency and response time are often used synonymously, but they are not the same. The response time is what the client sees. Besides the actual time to process the request, the service time, it includes network delays and queuing delays. Latency is the duration that a request is waiting to be handled. Even if you only make the same request over and over again, you'll get a slightly different response time on every try. In practice, in a system handling a variety of requests, the response time can vary a lot. We therefore need to think of response time not as a single number, but as a distribution of values that you can measure. Let's understand response time in more detail. We must now try to understand response time with the following sample figure. In the figure, each gray bar represents a request to a service, and its height shows how long that request took. Most requests are reasonably fast, but there are occasional outliers that take much longer. Perhaps the slow requests are intrinsically more expensive. This can be for various reasons, for example, because they process more data. Even when all requests are expected to take the same amount of time, there can be unexpected delays. These delays might be due to various random issues like switching between tasks in the system, problems in network communication, pauses for memory management, reading data from the disk, or even physical disturbances like vibrations in the equipment. It's common to see the average response time of a service reported. However, the mean is not a very good metric if you want to know your typical response time. Usually, it is better to use percentiles. If you take your list of response times and sort it from fastest to slowest, then the median, or the 50th percentile, is the halfway point. For example, if your median response time is 200 milliseconds, that means half your requests return in less than 200 milliseconds, and half take longer. In order to figure out how bad your outliers are, you can look at higher percentiles, the 95th, 99th, and 99.9th percentiles. High percentiles become especially important in backend services that are called multiple times as part of serving a single end-user request. It takes just one slow call to make the entire end-user request slow. There are algorithms that can calculate a good approximation of percentiles at minimal CPU and memory cost. Now we will discuss on various strategies to cope up load. An architecture that is appropriate for one level of load is unlikely to cope with 10 times that load, especially if you are working on a fast-growing service. People often discuss a dichotomy between scaling up, vertical scaling, moving to a more powerful machine, and scaling out, horizontal scaling, distributing the load across multiple smaller machines. Distributing load across multiple machines is also known as a shared nothing architecture. A system that can run on a single machine is often simpler, but high-end machines can become very expensive. Therefore, very intensive workloads often can't avoid scaling out. In reality, good architectures usually involve a pragmatic mixture of approaches. For example, using several fairly powerful machines can still be simpler and cheaper than a large number of small virtual machines. Some systems are elastic, meaning they can automatically add computing resources when they detect a load increase. Whereas other systems are scaled manually, a human analyzes the capacity and decides to add more machines to the system. An elastic system can be useful if the load is highly unpredictable, but manually scaled systems are simpler and may have fewer operational surprises. The architecture of systems that operate at large scale is usually highly specific to the application. There is no such thing as a generic, one-size-fits-all scalable architecture, and formally known as magic scaling sauce. The problem may involve the volume of reads, the volume of writes, the volume of data to store, the complexity of the data, the response time requirements, the access patterns, or usually, some mixture of all of these, plus many more issues. For example, a system designed to handle 100,000 requests, each 1 kilobyte in size, looks very different from a system designed for 3 requests, each 2 gigabytes in size, even though the two systems have the same data throughput. Now, we will talk about maintainability. Maintainability. We can and should design software in such a way that it will hopefully minimize pain during maintenance, and thus avoid creating legacy software ourselves. To this end, we will pay particular attention to 3 design principles for software systems: operability, simplicity, evolvability. Now let's see what these 3 mean. Operability. Make it easy for operations teams to keep the system running smoothly. Simplicity. Make it easy for new engineers to understand the system, by removing as much complexity as possible from the system. Note, this is not the same as the simplicity of the user interface. Evolvability. Make it easy for engineers to make changes to the system in the future, adapting it for unanticipated use cases as requirements change, also known as extensibility, modifiability, or plasticity. Thank you all for tuning in and spending your valuable time with us today. It has truly been a pleasure to share insights and knowledge on this platform. I also want to acknowledge the wealth of information and inspiration that has contributed to the content of our discussion. The insights shared today have been gathered from various esteemed sources, all of which are mentioned in credits section. Each article, research paper, and expert commentary has been instrumental in crafting a comprehensive and informative presentation. Thank you once again for being an amazing audience. See you in the next video. For any questions, you can reach to me at byteboss0073@gmail.com, and please subscribe to our channel at BitSize Bits.